Hello, everyone. My name is Sergey Maschenko. I'm an HPC analyst with SharkNet and Compute Canada. Today, I will be talking about our debugger DDT. And here's how you can reach me, my email. And throughout this presentation, I'll be showing some of my example debugging code. For those interested, either now or later, you can get them on our Git repository. You can always ask questions in the chat. Paul, the host, will be lurking in the background answering your questions, but there will be time for proper question and answers at the end of this presentation, which is roughly 1 hour long. All right, so the plan is I'll go through a few slides, and this is an outline of my slide. So I'll talk briefly, I'll give you an overview. I'll discuss about setup of DDT on our clustergram, provide helpful references if you need help with DDT, cover very, very light and not difficult at all setup you need to do to be able to use our debugger. And hopefully most of my time will be spent going through some code examples and sort of you'll be learning on the go the different features of our debugger DDT in live demonstration. So the overview. DDT wasn't originally owned by Alinea, and that's why you still might find references to Alinea in our setup. Like environment, once you load the module, you will see environment variable actually has Alinea part of the name, not ARM. But it was purchased by ARM, well-known ARM company, a CPU manufacturer, 2 or 3 years ago. So now it is with ARM. So what it is a powerful, not just parallel, but also serial. I will be emphasizing this point repeatedly today. It's super useful for any kind of debugging, including serial, parallel, and very, very special and unique feature, hybrid debugging. It has a nice graphical interface. We've been using it in SharkNet for almost 15 years now. And one of the reasons we picked it versus other competitors because it had really nice, very non-steep learning curve. So if you're a beginner, you don't really need to read any documentation. You just launch it, and it's very easy to launch once you made the minimum setup. And then you just learn on the go. So you basically, it gives you all the suggestions and tips and hints. It has very nice polished GUI. So I'll be showing that a bit later. So what kind of parallelism is supported? Going all the way from none, from serial codes, to pretty much everything else. MPI, which is distributed parallel computing, then multi-threaded, OpenMP is example, and a few flavors of GPU coding, including CUDA coding. Very special feature, it can also debug hybrid codes. For example, CUDA plus MPI plus OpenMP. It's entirely possible. It's gonna be quite complicated. You'll see all kind of extra GUI elements because there's so much parallelism going on, but it is possible. And that's sort of puts it aside from most of other debugging programs you may have encountered. And in terms of programming languages, this is primarily HPC type of debugging, like C, C++, and Fortran, including all the most recent flavors and versions. It has very limited support for Python, basically C Python 2.7. So it's not too useful for Python users. And in terms of models, parallel models, it's MPI, but also UPC, Unified Parallel C. Parallel features of modern Fortran, like co-arrays. And in GPU languages, it's not just CUDA, but also CUDA Fortran, also OpenMP accelerators, and HMPP. Interestingly, OpenACC doesn't seem to be included in the list, but I think CUDA would be probably the most frequently used for GPU debugging. DDT is installed on our clustergram only. There is a side comment here. So Niagara cluster has a much smaller CPU-only license for DDT, and the instructions are slightly different. I believe you say module load DDT on Niagara, and then you can gain access to small CPU-only license. But on Gram, SharkNet has a large 512 CPU core CPU license. And we have a second separate license, which is GPU enabled. It's only 8 GPUs, but it's less frequent GPU debugging, so seems to be fairly sufficient. It is not used much. So this 512 means it's across all the users at any given time, but because the usage is quite infrequent, hopefully this will change after this webinar, it's entirely possible you may in fact gain access to all 512 seeds if you ever have to debug such a giant code. The different question will be, can you actually allocate 512 CPU cores easily enough for interactive use? But in principle, you can debug very large parallel codes on Gram using DDT. So the CPU license can be used for any codes except for GPU codes. So you can use for serial, parallel, and hybrid. And to use it, you have to load corresponding module, which is module load DDT-CPU. It is strongly advised you to make sure you're running the current, which is now default environment, standard environment /2020, because only this way you'll ensure you are using the most up-to-date version of DDT. The GPU license, which is much smaller, but it can debug GPU code and CPU code. So if your code involves GPU in any capacity, either it's CUDA code, or a hybrid code, or whatever, you should be using this second license. And you say module load DDT-GPU. And the only difference between these two module load commands, you are accessing different license, but the binary is the same. It points to the same package. I already mentioned the Agro cluster has a 64 CPU core, CPU only license. All right, so as a beginner, of course, you want to know where to find help about DDT usage. I already mentioned that DDT is fairly self-explanatory, so you don't, in my practice, I very rarely had to look up anything in the guide. But if you need to, either Google for DDT ARM guide, and currently this is the link to the latest version of the user guide. The same guide as a PDF file can be found on our cluster once you do module load command, module load DDT-something. And the pointer, the path is described by this environment variable. And remember, I told you Alinea is still being used by us for some cases. So it's ebroot alinea/doc directory. You probably want to copy PDF file on your computer, and then you can view it locally. We also have some documentation on Docs Wiki. This is one of them. I can probably just show you. So let me see where I am. Okay, so if you go to docs.computecanada.ca, and if you search for DDT, that's the only page which comes up, which is, it's called ARM software, but it's basically DDT page, and that's why it's redirected from DDT. It describes basic setup, nothing advanced. There is also a tutorial, which I wrote some time ago. It needs to be slightly updated for a newer version, but it's probably quite thorough. It's comparable to the material we're going to hear today, maybe even more detailed, and it has quite a few screenshots, so you actually see all these elements visually. So, so there are options like that. So there are two wiki pages we have. In the past, I also did similar or webinars on DDT topic, and you can look for them on our YouTube channel. Just make sure they're no more than 2 or 3 years old, because otherwise they're probably outdated. And you can always send an email to our ticketing system, support@computecanada.ca, and feel free to mention my name, Sergey Mashenko, because I'm the person in charge of DDT in SharkNet. So setup. So there is a very slight complication compared to typical packages you use on Gram. And Gram is just one of the national systems, but DDT is only installed on Gram. This is one of the few differences. Otherwise, national systems have very similar, identical software packaging. The slight complication is that it is interactive. Of course, it's debugger, and it's using GUI, graphical user interface. And that makes it just slightly more complicated. Basically, you need to figure out how to have a GUI access to our cluster. Once you've done with that, you don't have to worry about it ever again. So there is a a small setup step you have to do if you never used DDT on our clusters. And I will describe basically a couple of possibilities of using DDT on Gram. So by far the easiest way and highly recommended is to use so-called X11 forwarding. This is a feature built into Linux system, which our clusters are running. And if it works for you, just use it. There is another way I'll show a bit later. It's called VNC. If X11 forwarding is too laggy or too slow, then you may consider, but it's quite a bit more involved. The beauty of X11 forwarding, it has essentially zero setup. So it's very quick, and that's a huge advantage. And it works fine. So I'm under Windows using standard cable internet. I don't see any lag at all. It works very well, and as you will see today. So the initial small setup you have to do, if you're under Windows, we strongly recommend to use MobX term free application, which probably have already used for SSH connection and SCP feature. Another great advantage, it has a built-in X11 forwarding, and it's already enabled by default, so you don't even have to do anything. You install MobX term, you run it, and you connect to a cluster, and you can run DDT. It's sort of Swiss Army tool for Windows users of Compute Canada facility. For Mac, you use your standard terminal, but for X11 forwarding, you need to install free app. It's called XQuartz. For Linux, everything you need is already there. Once you've taken care of that, let's say you have MobX term, I'll be showing it in a moment. I'll be using it myself. The only difference compared to your usual way to SSH to a cluster, you say SSH -Y. This is what enables X11 forwarding. I believe on MobX term, you don't even have to do that. It's enabled by default. But if you're on Mac or Linux, you most likely will have to do that. And then you test whether it works or not, your X11 forwarding. After you log into our login node, you execute one of the GUI command like xterm, for example. If it works, it will open in a separate window. Sometimes it may be in the hiding, so you have to, maybe it's minimized, maybe you have to open. So check your taskbar. But if it doesn't, then there is a problem with the X11 setup. So you basically either forgot to put -Y, or maybe if you use MobX term, maybe it's disabled for whatever reason. So you have to investigate why your X11 forwarding isn't working. Okay, and if you just want to do a quick test of our debugger, it is perfectly fine, but only for CPU codes, only to run a quick test of DDT on the login node itself. So all you need to do now to module loads or DDT-CPU, and then you run DDT command space path to your binary. I'll show a bit later how exactly it works, right on the login node. So for a quick test, a few minutes just to see if it works, or maybe you have very simple debugging issue. So that's perfectly, it's allowed to do it on login node. For anything serious, for real actual debugging work, you have to allocate interactive compute nodes using salloc command. So for those who never heard about salloc, never use interactive nodes, this is the feature of all national systems. So if, for example, you for sure know how to submit jobs using sbadge, and sbadge takes a job script, and inside job script, you provide one switch for the sbadge per line. And it always starts with $, capital sbadge, and then a switch. So salloc, takes practically the same commands as sbadge, but the only difference, you don't provide them in a job script, you provide them in a command line. So you see the familiar switches, your requested runtime. So I'm requesting 1 hour runtime for my interactive session. How many nodes? I'm requesting 4 multi-threaded cores. So this is for multi-thread, it will not work for MPI and vice versa. For MPI, you would say -n, small n, and then 4. Total amount of memory. For MPI, I would say mem per CPU. And obligatory argument, your account. It can be either your supervisor or your own, or maybe a rack account, whatever is available, you use that. So that gives you access after some wait time, depends how much resources, to a special subset of nodes, compute nodes on Gram, which are reserved for interactive use. Sometimes you get access almost instantly. Sometimes you have to wait maybe half an hour, 1 hour. It depends if you ask for lots of resources. So it's already good for all kind of profiling and testing, but specifically for GUI application like DDT, what you have to do before you execute SL, you have to add this --x11. This because asaloc command will take you further down from login node to compute node. So, and that asaloc needs to know that you also need x11 forwarding for this second leg. If you forget to put that, you cannot run GUI applications inside compute node. So if you run this command and get error like this, x11 connection rejected because of wrong authentication, most likely, or at least one likely reason, is that your home directory has two lax permissions. Basically, it cannot be readable by anyone but you. Readable, also X, and writable. So you basically have to remove all those extra permissions for the time when you need debugging. And if you wish, you can restore them later. So asaloc-x11 is very strict in that respect. So if that approach I just described works for you, it's not super laggy, that just use it. It's very simple. And you can run any size jobs because you can use actual asaloc command, allocate. If you need 512, in principle, you can do that, 512 CPUs. If you need GPU, you can use it on GPU nodes and so on. But if for some reason, you have fairly slow internet, doesn't work for you, a better approach, but more complicated, is so-called VNC. And for that, you need to install very specific VNC viewer. There are different versions. There is tight VNC, real VNC, etc. But we only support Tiger VNC. Make sure you don't install the server. Viewer comes as a separate binary. So they have binaries for Windows, Mac, and Linux. And then it's very simple. You launch, there is a tiny window I'll be showing you. And all you need to do, enter this address, which is gra-vdi.computecam.ca. So what is this about? So this is the address of, I think there are two special nodes set aside on Gram. They're part of Gram cluster. But unlike our login nodes, for example, they have special GPUs. They have multiple GPUs. They're not super powerful. They're not good, for example, for CUDA applications. They're more like for visualization. These are GPUs for basically accelerate your GUI application. And DDT is one of the GUI applications, so it's perfectly fine to use these special nodes for debugging. So they're shared, and they don't have schedulings, so you cannot submit jobs from them. So what you can do, you can run things on gra-vdi. And because they're shared, sometimes may get slow, and maybe your job too large it's not gonna fit on gra-vdi. But there is one possibility. Also, only CPU codes, because the GPUs are installed there, but they are the kind which you cannot use for CUDA debugging, unfortunately. And VNC can so this is easy, actually. It's easy, but somewhat limited. VNC can also be used to connect to a compute node to run, for example, DDT. This is significantly more involved. So please look up this VNC wiki page on our docs wiki server. It's fairly involved, so I don't know, it would take 5-10 minutes maybe to set up. So only if X11 doesn't work for you and really want to use VNC on a compute node, then you probably want to go through these extra steps. All right, once that's taken care of, then the rest is super easy. So now you're ready to debug a code. As with any debugger, you have to prepare your code. You can't just run debugger through your binary, which you already have. Well, in fact, you can, but it's not going to be very useful. Much more useful is to recompile your code with a special flag added both linking and compiling stages, -g. And the same flags can be used for different compilers, ICC, GCC, other compilers. And then you have to say what kind of level optimization you want to use. Usually you say -O, this is capital O, and then 0. This is the typical situation. So you do that unless you know that the bug you're investigating is optimization level specific. There are some bugs, in fact, I might be able to show you one, which does not manifest itself at 0 optimization level, but is triggered when you use anything above 0. In that case, you don't have a choice. You have to use -O, 1, or 2. And the reason the reason it's not ideal, because debugging becomes less straightforward and linear. So if you're trying to step your code, I'll show you later, if optimization is anything but zero, the trying to step through the code becomes kind of non-linear. Sometimes it jumps back and forth because the code has been optimized. So it becomes slightly confusing. But if you have to, then you use whatever optimization level you need. For CUDA code or hybrid code using CUDA, you have to add both the one I just described for the CPU part, and for the GPU, don't forget to include -G during compiling and linking. By the way, what happens if you forget to put this or this? You still can run DDT, it will open, but instead of seeing the source text inside the main window on DDT, you'll see it in a couple of minutes, you'll see a message warning that you probably forgot to compile it with -G and -G. So that you just have to recompile your code and run it again with DDT. That's it. So once you recompile your code, then the way you run it with DDT, you just pre-pan DDT before the binary. Very conveniently, even if it's MPI code, you don't have to use MPI run -np, etc., etc. You still have to say DDT space and path to your MPI binary or hybrid binary, followed by optional code argument. So all these extra commands, arguments, how many CPU cores to use, etc., you can specify in the GUI interface. And I'm approaching the end of my slide deck. So I'll be showing you some code examples, which are located in this folder on Gram. Currently, it's not readable by you, because remember that X11 forwarding breaks if it's readable by other people. So I had to disable for now, but I will re-enable after this presentation. Or you can just download from our repository, debugging exercises. There are a few folders there. I don't think I'll have time to go through all the examples, just some highlights. So I have a few very simple serial buggy code example, OpenMP, MPI, CUDA, and CUDA also includes one hybrid, for the heck of it, CUDA plus MPI example. All right, so it's time to switch to live demo. And before part of my live demo will be first showing you VNC way of connecting, and then I'll just switch to standard X11 forwarding. So I'm sharing my whole desktop. So what I'm gonna do, I'm gonna hide my slides, hide the browser. Here's my desktop, which has a nice sort of swimming pool background. And what I'm gonna do, I'm gonna open my application Tiger VNC viewer, just a second way to connect, and then I'll switch to the main way, X11 forward. So after I open this application, it's very simple. You don't have to modify any options. All we need to provide gra vdi compute.ca address, and then you click connect, and it just works. So you can do it full screen. I'll probably just open it wide. It looks slightly broken. It shouldn't matter. And then you use this is a Linux desktop login. You use your Compute Canada credentials. So SYM is my Compute Canada login name. Oops, I probably misspelled it. Yep. All right, so, and now you have just a Linux desktop. Read carefully, there is a warning here. Basically, you cannot access any of the Compute Canada modules unless you executed two commands. You have to load ccenv. Oh, it has a bit nasty feature of disappearing, but I'll show you. So first you open the terminal, and then I'll probably have it in my memory module. Okay, so this is the command I would use. So first you load the environment, module load ccenv. This is obligatory, and then you can load the standard environment. So exactly in this order. And now you have access to our standard software stack, and these are the default modules. And then, as you can see, this is a 2020 standard environment. And then I can module load, let's say, well, it's only the CPU version we can load. The GPU version doesn't work on VDI nodes. So we load it, and then we can just launch DDT using, ignore that there is some error, but basically you click run, and then you run your command. I will be showing it more slowly in a second. But this is the way to run DDT on sort of VNC approach. But as I explained, a more convenient approach is to use X11 forwarding. I'm under Windows, so I'm using Mobile Storm application. I open local terminal inside Mobile Storm. It's not default option, but I just like to enable that. And then you can type the standard commands like SSH, my login name at gram.computecam.ca. Normally it asks you for password, but under Windows, you can set up mobile terms that's using public key agent, so I don't have to type it every time. And okay, so we are on gram login node. As I mentioned before, you already can run a quick test if you wish. By the way, you can test if X11 forwarding works. So I type xterm, and sometimes Windows opens it on the bottom, and it may take a bit of time. So let's see which way it goes. Okay, it opens. Sometimes it's minimized, sometimes it's not. It's hard to tell. But yeah, it works. So if it didn't, it would give you an error message. So it works up to now. And now what I can say, module load DDT CPU. And then I can launch my DDT either by itself or with a binary as a second argument, my code binary. This is just to show you how it looks like interface. All right, so, and now it's time to, well, I think I want to show you using SL. This would be more a proper way to use. So all my exercises. So I'm going to look up my SL command. Sorry, ignore there is huge, many times I used this command before. And I probably want to allocate a GPU node, so I can show both CPU and GPU codes. Well, actually, I don't think I can, but anyway, so because if I allocate it for MPI use, I cannot use for open threaded, but OpenMP, but anyway, so let's maybe do this way first. All right, and total memory, I'll say 0. So I want to allocate the whole node, and critically, I have to say --x11, and I'm allocated for 1 hour. Let's see if I can gain quick access. Yeah, so it was a quick access to these, the whole node, compute node, which has GPU, in fact, 2 GPUs, but I asked for 1, which I guess wasn't really important for my presentation. Okay, so now I'm inside the compute node, and now I have to test to make sure my X11 works. I'm going to run xterm again. So if my home directory had 2 lax permissions, I would get error message at this point, but now it opens up. So X11 forwarding works from me to login node and from login node to compute node. So there are 2 legs of this journey, and it works all the way. So it's all great. So we are ready to dive into some of my code examples. So I have this debugging exercises subdirectory, and I'm going inside serial. So there are a few codes. I'll be showing you a couple of them, and FPE is one of them. And just have a look using Nano Editor. This is a very simple program which has 2 kinds of division by 0, and you definitely don't want your code to have division by 0. What is interesting, I think I discovered early on when I joined SharkNet, started using DDT, that by default, division, floating point division by 0, like in this example, they are not caught by our compilers, and therefore they're not caught by debuggers. They just ignore it. What happens, the y would be assigned NaN, non-numerical value, and the code would happily continue crunching numbers and making a mess, right? Because you don't want, in normal research code, NaN numbers are not good numbers. So my advice for anyone doing C code, C++ code, you have to do 2 things in your code. Somewhere in your main or header file, you have to include this header file, f environment.h. It's a Linux thing. And then you somewhere I think somewhere in the main code, it's sufficient to include this special function, fee enable except. And then you list the exceptions you want to capture, the ones which are not captured by default. And the one I'm particularly interested in is division by zero. These are true floating point division by zero. Interestingly, Linux has what it's called floating point division by zero, which is not floating point, which is actually integer division by zero, which is of this kind. These are caught by default. But for actual floating point, you have to do these two steps. I also want to capture like square root of negative number or overflow. These are not good to have in your research codes. You want to capture them. And you would be surprised if you run your typical research code with these enable, you might be surprised how many problems your code may have. You probably want to fix those right away. So, so with these two line additions, now it should be able to capture this problem. If I comment this out, it will not be captured. It will only capture this one. All right, and let's compile it. So to compile for debugging, we're gonna use ICC-G, and I will be normally using 0 optimization level. It will produce a out binary. And because we added those extra 2 lines, it will be caught even during just a regular run without debugger. It will tell me it's a floating point exception, core dump. And now we already load the DDT debugger module, so we can now run it with DDT software. All right, so if you already added binary in your command line, it will right away open this window for you. And it's pretty good. Usually it auto detects whether it's just serial code, or if it's MPI, it will auto put MPI, OpenMP, or CUDA is not actually possible here because the license doesn't allow. I need to load different module for that. Also, there is optional memory debugging. I'll show it later, and you don't have to worry about other things. So you can always override if you think it's wrong, but in my experience, recent experience, it's always good. It always auto detects correctly. So now it knows it's serial code. So all I need to do is to press run. All right, so we are now seeing the main interface. And what I like about DDT, all the important stuff is already in one large window. So everything you need is already here, or most of things you need. So what are the main elements? So the main elements are the most obvious one, here's the text, the source file. So if you have multiple files inside the code you compiled, then you will see on the left side, you will see the source code browser. So here's only one. So, and then you just click wherever you want. You click, and if there is so you click on the file or click on the function, it takes you right away. And it can open multiple tabs. So it's very convenient. You can switch between different files very quickly. So the source files displayed uses nice syntax highlighting colors and also the font. So you can easily differentiate between comments and macro commands and the actual code. And okay, so what else important? On the right side, you see there is it's the viewer of the values of the variables, okay? And for example, I can click on any variable if it's already, as long as it's already been declared, or sometimes, yeah, maybe not, it doesn't even have to be declared, but because it hasn't been initialized, you see some crazy values, but these are listed here. A tip, if you want to see multiple variables belonging to multiple lines of code, you can drag with your mouse, left mouse, and then you can see multiples. Or, which works for fairly small codes, you can just look at all the local variables in a single window. The global variables will not be shown, by the way. You would have to use other mechanism to see their values. Another important window is evaluate. I already added something here. So let me just switch this over. So you can just delete this. It remembers from the last time you ran. Basically, If you don't want to just see variables, or you want to see variables not necessarily on the line you're currently at, you can right click on the evaluate window and you add any valid expression for this particular language. So you can use functions like square root or whatever, any combination of different variables. You can reference, do reference pointers, etc., etc. You can do you can view elements of the arrays and structures, you whatever, any valid expression, and it's going to be constantly displayed here as you go through your code. Navigation through the code is here. So initially at the very first executable line inside your code. So what you can do, how can you go through your code, how you can debug it? There are a few ways. Simplest is to, it's like MP3 player. You press play and it will run and run and run until you press pause. This is super useful if there is a bug which is automatically captured. Like in this case, there is a floating point exception, which is something a debugger can capture, and it will automatically pause on that particular line and tell you the description of the problem. Alternatively, you can step over functions, or you can step inside function, or if you're inside function, you can step out. Sometimes you run, then pause, and then you step, and then you run again. So you can use any combination. And a third way to navigate, you go to the line of the code where you want to get to. You click there with the left mouse, and then right mouse click, and you can say run to here. For serial code, it's equivalent, but for parallel code, it does something else. This third way of navigating also tries to synchronize as much as possible all your threads or ranks if you're using MPI code. Okay, so let's not to slow down too much here. So let's use it as MP3 player. I'm going to click. All right, so it auto-detected my bug because it's an easy one. The one which generates a segfault or something which a debugger can capture. It's the easiest to deal with because you just run and it pauses there and it tells you what kind of a problem you have. It's a sig FPE, arithmetic exception. You can pause. If you try to continue, it will fail. In most of times it will, but you pause and you look around, you notice that X is 0 and you're trying to divide by 0. So it's very obvious something going on, and here's the problem. So you solve your bug. So that was easy. Yes, okay, so let's switch on to another problem. And I think I want to skip, no, I'll very briefly show memory debugging feature. So let me go back to my MobX term. I can put it in the background and go, no, I still want to stay here. So I have very simple memory leak problem. I have a loop and I'm calling a function where I keep allocating things and I forget to deallocate them. So let me compile that. For memory debugging, you normally want to enable optional feature of DDT, which is called memory debugging, conveniently. And so by the way, how do you restart? So there are two ways. You can go here and you can say new session, and that will allow you to change features. Like if you want to enable memory debugging, this is the only way to do it. But if you don't want to change anything, you don't want to change memory debugging, you don't want to change number of CPU cores, etc., you just say restart session, and then it will just reuse the same input parameters you used first time. In this case, I want to enable memory debugging, so I do file, new session, run. So that's what I'm trying to do. Yes, I want to exit the current session. Yeah, I accidentally typed it, but I don't care about that. Small edits I did. And now it will restart. And the only difference, I want to enable memory debugging. You can see there are a bunch of things you can change, what kind of memory debugging, but by me default is fine. And I'm going to run now with memory. Usually you want to keep it off because it takes more resources and can be slower. And by the way, sometimes it's a good idea to pay attention to warning which DDT produces. Sometimes they're useful, sometimes less useful. And here's the example. So I have a loop where I'm calling a function which keeps allocating stuff and forgets to deallocate. And you see, it forgets because I commented out. So I'm not deallocating. So what should happen? So memory leaking is a bit harder to see. First, probably you want to run until the very end. So I'm showing here a next useful feature of any debugger is breakpoints. So the list of breakpoints, you can find it here on the bottom. You can create breakpoints different ways. One of the ways is to click with the left mouse here. And this is non-conditional breakpoint. That's why just a solid circle. If you add any conditions, and you can do it here, it will have small plus sign here. So you know it's conditional. And in this case, it's non-conditional. I just want it to pause before it actually ends. And so you see it's already here. And now I want to show you, there are multiple windows you can use. I like to use overall memory stats. And in particular, yeah, this window is fine. So orange is allocation calls, green deallocation calls. I have allocated 800 kilobytes of data and haven't deallocated practically anything. I am already at the end of the program, so I did something wrong. You can further spot this, and I'll show example of conditional breakpoint. You can go here and create another breakpoint, but now the condition, my variable index j, and you use the syntax of your language. So it's C, I'm using j equal 1, for example. And then I have to restart. Every time you reach the end, you have to restart. Don't do new session, just restart, unless you change some major parameter. So you restart, and now you can play. Okay, it's still here. And okay, so so j, variable j, by the way, you can add j. For some reason it didn't work as conditional. Wait a second. Conditional j equal 1. Interesting. So anyway, I can always add a variable I want to watch to evaluate window. So I expect it to be, okay, let me redo. Oh, sorry, I added condition in the wrong line. Okay, yeah, sorry about that. So j equal 1 should be, well, in this case, yeah, okay, let's do it 1. So now it's conditional, it has plus, so I can run. It's very convenient when you have bug which happens, let's say, at 1 millionth iteration of your loop. So you just put a condition. So j is actually 1 now. And if you have a look at the memory stats, you already see there is, there is 1 kilobyte allocated, nothing deallocated, so nothing major here. And then you say, for example, 100, and it goes up to 1,000. So I click run again. So I'm here at 100. And if I go and look at the memory stats, it went up proportional. It's 80 kilobytes, still nothing deallocated. So then you kind of think, okay, that must be the memory leak happens inside this loop. So unfortunately, memory leak is not something you just run and it will pause and tell you, memory leak. No, you actually have to sort of zoom in. You have to do a few runs of your code until you zoom in into part of the code which is a culprit. And once you fix that culprit, you will be able to get rid of this memory leak. All right, so switching to, so what else I wanted to show? I think I'm gonna switch out of bounds example, and let's show at least one MPI or OpenMP example. Let me see actually which one I can show, because I allocated for multi-threaded. Yeah, so I can actually do OpenMP. Just very quickly. And what I want to show you, deadlock single. It's a very simple bug, and it's fairly common for multi-threaded programming. And what happens, I'm using the work sharing construct. Sorry for those of you who don't know OpenMP. It's going to be very sort of not essential, but basically in OpenMP, if you have work sharing construct like for single sections, this statement has to be reachable by all the threads inside your parallel team of threads. But here it's not possible. And okay, in fact, here, so single is also work sharing constraint. So it's not possible for all threads to reach this pragma because I have if statement. If my thread ID is 1, I do this pragma, which is not allowed. It will not complain at compile time, but you get a deadlock. So the code will just hang there. So let's first demonstrate it happens. So this is OpenMP code. So I have to add, it's with Intel, it's -q OpenMP. Okay, so, and that should do it. I'm going to compile the code. And this created multi-threaded binary. I can run it as usual. And I have a deadlock. It doesn't proceed. So I can kill it, run it again. It never proceeds. With OpenMP, deadlocks are not super straightforward to identify, even with DDT, but I'll show you it still helps a lot using the DDT debugger. So let's do that. Or sometimes it's minimized, so I have to open it here. All right, so it auto-detected that it's OpenMP. Nice. We don't need memory debugging, and we want to use it with 2, or probably more, let's say 4 MPI threads, and we just run it as usual. And so this is OpenMP. You only create teams of threads, parallel threads, once you're inside parallel region, and we are currently outside. My current state is outside. So that's why here's the new feature. So this is the bar where it shows different threads. It can switch between different threads. So as tip for OpenMP debugging, you cannot just step into one of those parallel regions. It's not going to work. So you have to use the trick. So you basically set up a breakpoint. So if you set up a breakpoint and run, only then, you see there are multiple threads, 4 threads, and you see you're inside the parallel region, and you can switch between the state of each thread. And because it's a solid bar, that means they're all in synchronous state right now. Once you see multiple, well, there is kind of non-synchronous thing here. And by the way, another useful feature on the bottom, you go to the stacks, and then you can see, so it shows you instant snapshot of the current state of your program, multiple threads. You can hover the mouse and you see which thread is on each part, which particular line inside code. Some of these lines are some system level code. You can also hover mouse here, and it will show you also, again, this sort of snapshot view where each thread is, or which threads are on this particular line. Anyway, so so that's, you can switch between threads. You can change focus. If you start stepping through your code, it will try to do that synchronously for all the threads. Sometimes it works, sometimes it doesn't. You can change focus, and then you can operate each thread individually. So you can switch to thread 1 and then start stepping through. Sometimes it works, sometimes it doesn't. Depends on your code and depends on the thread. But basically, there is a possibility to desynchronize and operate each thread and also each MPI rank independently. And so back to the bug. So I'm gonna, okay, I'm gonna remove this breakpoint. If I just run and wait, and by the way, here's the input output step. So you can see what's the output of my code. So it's hanging there. So this is deadlock. You press pause, it's hanging. You press play again, it's still hanging, pause. So you're stuck. And every time you are running, you can see all the running threads are green. The pause threads are orange. Sometimes some of them are paused, sometimes not. Others are not. So it can be a mixed state. So in this particular case, it's not super obvious what's going on here. So you're stuck. You're always at the same lines of your code. And this line tells you there is one process and thread number 1. And here tells you the process thread number 0. So yeah, as I said, it's not super obvious in OpenMP. It's more obvious in MPI deadlocks, but you should be able at this point to identify that there is a problem, there is a deadlock, which involves, this particular work sharing construct. Unfortunately, it doesn't tell you here's the problem. No, it doesn't, because that's not how OpenMP works. But debugger already allows you to look around to see where you're stuck, on what particular lines you're stuck, and sort of figure it out. All right, so there is not much time left. I think in a short time left, I want to show you some sort of MPI code. So I think for that, I'll have to exit. And because MPI, I need to say -N32. And maybe, in fact, maybe I'm going to show the hybrid code. So if I go to CUDA, sorry, debugging. All right. So there is a bunch of buggy codes here, CUDA code. There is also a separate directory with MPI code, but I'm going to show you the hybrid code just for you to get an idea how it works. It's a bit tricky to compile, so I'm going to refresh my memories. So I'm going to execute the whole command. And of course, I have to say module load CUDA first, and also DDT-GPU. I need the second version of DDT module. And I execute this command. So remember, I have to add small g and capital G for both CPU and GPU version of the code to enable debugging. So, and this is just a work, it's not a buggy code, so it works. So this compute node has GPU, and it's a reduction example way, or actually, it's a hybrid. So I have to say MPI run -N2. So there are 2 GPUs. I believe that's what I have to do. Okay, I'm doing something wrong here. Okay, I think so. Let me just try. I don't have much time, but let's, if I can, I think I need both GPUs for this thing to work. So let's try again. So debugging CUDA. Okay, and MPI run. That's the one I want to. MPI run -N2, and then, so that's, yeah, it worked. So so this code actually uses 1 MPI rank per GPU. So I needed 2 GPU to be able to use 2 ranks. So it's a hybrid code, multi-GPU hybrid code. So and to debug it, it's actually easy. You just, again, all you need to module load DDT-GPU, and then you prepend, you prepend your binary, and that's it. No MPI run, nothing. For hybrid or MPI or any other kind of code, this is all you need to do. So it again, open minimize. So I do this. So it auto-detected that it's both MPI, I'm going to use 2 ranks, and it's CUDA. Nice. And I'm going to run. And this is the most complex interface you'll see, just to give you an idea. So it's trying to connect to both ranks, CPU ranks. The GPUs are not enabled yet. Here is, because it's MPI call, there is instant access to one or the other MPI rank. So this is a navigator of MPI ranks. And at the point where you reach inside the GPU code, which is a kernel, you can, as usual, put a break point, for example, inside your kernel, and then press play. So what happens? Once you're inside a kernel, you'll see dual navigator. You see, you can switch between different MPI ranks, and that also switches the GPU I'm currently using. But within particular GPU, it just happened that block number 33, thread 0 was the one which paused first, reached the breakpoint first. But in principle, you should be able to switch blocks and go. You can switch to a different thread and go. And so you can navigate both in terms of MPI ranks and both in terms of GPUs, and also block and thread inside the block. If your code is even more complex, it uses OpenMP, for example, then you'll see all 3 navigator bars for MPI ranks, for threads, and for GPUs. So you can go as crazy as that. Of course, it's more difficult to debug, but the idea is still the same. Even with this complex hybrid code, I go inside, I highlight, By the way, another tip here, GPU is very forgetful. It doesn't have much memory to keep old results. So if you try to look up old result, most likely you will not see it unless it's something which is used in further ahead. So it very quickly offloads whatever variables you use. So typically in GPU code, you only see the current variable result or the variable which is heavily used before and after then. So it's trickier, but it's still possible. And you can go through, you can run, you can set breakpoints, you can set watch points. I didn't have time to discuss that, unfortunately. But it is possible and quite convenient to debug hybrid codes using DDT. So I reached the end of my time. Thank you everyone for your attention. And now it's time for questions, if there are any.